start with the last problem in the section from Friday. It's a review of what we did on Friday, but we didn't finish that last problem. So we'll start with that one. Okay, here we go. Water is being pumped into a tank at a rate modeled by W of T equals liters per hour for time between 0 and 8 seconds, where T is measured in hours. Water is removed from the tank at a rate modeled by R of T, where R is differentiable and decreasing. Select values of R shown in the table. At time T, there are 50,000 liters of water in the tank. Estimate R prime of 2. Show the work that leads to your answer. Indicate the units of measure. And then use a left Riemann sum with subintervals that they give to us to estimate the total amount of water that is removed during the 8 hours. Okay? We actually are not concerned about W in this problem. I'm willing to bet this was a 2016, there were probably two other, like a C and a D parts to this question, but we're just doing these two parts because they relate to things we already know how to do. If you don't know the derivative and you are given a table, you can approximate the instantaneous rate of change, aka the derivative, by using an average rate of change, aka a slope. So if I want to approximate R prime of 2, I'm looking at these two values because the average between 1 and 3 is 2. And all I have to do is calculate a slope formula. So 950 minus 1190 over 3 minus 1. And I get that this is R prime of 2 approximated, right? So R prime of 2 is approximately 380. Wait a minute. Did I lose my mind here? Yeah, I typed in my calculator wrong, guys, sorry, my bad. Was everybody like, wait, that math doesn't math? It should be negative 120. I'm sorry. I also noticed it was leaving the tank. Did anybody notice we are draining the tank and I got a positive value? That was what made me pause. Oh, and here's the next thing. If time is in hours, and the rate that we're measuring is in liters per hour, R prime of T is in liters per hour squared. So this is liters per hour squared. How do I know that? Think about the units. When I calculated the slope, I had liters per hour in the numerator divided by hours in the denominator. That's liters per hour squared. You can always go back to unit analysis. If you're not sure what the units are, write them down next to the values that you picked from your table, or write them down next to the values you picked from your chart. So that's the first part. Okay, and now for the second part, we're going to do our Riemann sums. So the Riemann sums, we're using a left Riemann sum, meaning the left side of our equation. And we're going to use the subintervals indicated by the table, meaning we're going to do, this is a left rectangle, this is a left rectangle. Each one of these are the left side of the rectangle, and the distance from here to here is the width of our rectangle. Okay? So for part B, our total removed is going to be our first width of a rectangle from 0 to 1 is 1, and our left side value 1340. Our second rectangle from 1 to 3 has a distance of 2, and our left side is 1190. Our next rectangle from 3 to 6 is 3, and our left side of that rectangle is 950. The next rectangle from 6 to 8 has a distance of 2, and the left side of that rectangle is 740. So I imagined that each one of those was the edges of the rectangle. I figured out the width based on the distance between the x's. I figured out the height based on the y's. And now I'm going to crunch those numbers and type it in correctly this time. I'm not done yet. How did I know that it was liters? When I multiplied an x times a y, I did hours times liters per hour. The hours canceled out and my answer came out in liters. You can always do that unit analysis. Next, is this an overestimate or an underestimate? So let's talk about what's happening in this equation, in this graph, in this chart. It's decreasing. From every step to the left to the right, water is going out of the tank, it's decreasing. That means that whatever this looks like is going down from left to right. As I'm doing my left Riemann sums, I'm going to end up always being over the top of the graph, so this is an overestimate. Okay, so we say since R of t is decreasing and we used a left Riemann sum, so this is an overestimate. Questions? What's that? I'm glad you asked that. So last night I was reading calculus teachers debating on the internet, as they do, and Mark Curley, who is a famous calculus teacher, not to normal people, he's a famous calculus teacher and AP grader, and he got on a soapbox and told everyone that you should never use abbreviations ever. It's better for your students, it's better for the graders, it's better for everyone. So, long story, I would encourage you to, as much as possible, write things out fully. Short story, they probably won't mark you down if you say LRAM. They definitely won't mark you wrong if you put IVT versus MVT, but there's all kinds of brain science that says that you actually remember it better if you write out the whole thing, and you're less likely to make a mental typo. So like if you're writing IVT and MVT, it's real easy to mix up an I and an M. It's a lot harder to mix up the word intermediate with extreme, right? So I would encourage you to write out the whole thing. If you don't, you're probably not going to lose points as long as you're still right.
I feel like the AP grading, like it's like they should put out like a rubric for how what things you could write. Right? It feels like they're a little vague.
Okay. There are rubrics. And as we go into second semester, when we start doing more FRQs, there's grading guidelines, and they will explicitly say things like, if the student didn't give units, then they don't earn the point. If they didn't say IVT, then they don't earn the points. And there's also some room for interpretation amongst the graders. So some of it, unless you're in the room grading with them, you're just guessing on what they're gonna say is okay and not okay.
Okay, thank you.
So that's why I always try to give you guys, like, they will never mark it wrong if you write out Riemann sum, but they might if you put L. I don't know. Probably not. I'm not in the room.
Alright.
Okay.
I was you an AP grader, and then I was like, no, that's insane.
No. I probably will at some point in the future, but I am not this year.
No.
You want to miss, we're about to learn integrals.
Tell me the best moment is today. The best moment we're not. Optimization problem.
Okay, so here we go. Are you ready? We're about to discuss what an integral is. This expression right here, that nice little curly thing, looks like a cursive F with no line in it. This is read as the definite integral of 2t minus 1 dt as t goes from started with 0, from 0 to 4. So that symbol, this symbol right here is an integral. When you put numbers on it, it's telling us that we're going from 0 to 4 on whatever the variable the d is next to. dt, and then you have whatever this expression is in the inside, and that expression is the part that can change. Okay? So that's how you would read the sentence. Now we're going to draw the diagram of what the picture looks like. So this 2t minus 1 is velocity. So we're saying that v of t equals 2t minus 1. And the diagram looks like this. This is v of t. This point right here is where 2t minus 1 equals 0, or t equals 1/2. This was the intercept, where y equals -1. And here's what it means. If this is 4 and this is 0, it's asking what is the area under this curve between the curve and the x-axis. What is the area between the curve and the x-axis? And so that shaded area is essentially what we're trying to figure out. Man, if we're allowed to use geometry, that's easy. But we're going to use calculus. So to evaluate the expression,
Why do we learn it? Okay, dumb question. Why do we learn it with calculus if we can do it in equation?
so this picture is easy. Actually, we're going to do it with geometry first. This picture is easy to do with geometry. This picture is not. Right? So if we can understand that the geometry and the calculus give us the same answer, we can make an educated choice about which one makes the most sense for any given problem. More of our problems look like this than they look like a nice pretty triangle. Right? Okay. So here's the next thing. We have two different sections in this picture. We have two different sections in this picture, and we have been talking about velocity and position and what all those things mean. So let's think about what's happening for the values up here. We have a positive velocity, and it is traveling in a positive direction. What's happening over here? We had a negative velocity, and it was traveling in a negative direction. That meant that it was traveling in a negative direction for some of the time and a positive direction for some of the time, which means if we're traveling negative and positive, and you want to know what's the distance between these two, I can't add this plus this. I have to subtract in order to figure out the difference. So the values that are below this curve, this triangle needs to get subtracted away from the values that are above that curve. You can also think about this in terms of what the actual values are in this picture. So this, traveling from here to here, is -1. And I know that an actual triangle doesn't ever have a length of -1, but if you allow that to stay -1 as you calculate your area formula, you will see why this triangle turns out negative and this triangle turns out positive. So this one goes 3.5 by, and when you plugged in 4 into my original, 3.5 by 3. No, wait. 3 times 4, 8, 7. Sorry. Okay, so now to find the expression, to find the area, I'm going to do the blue triangle and the red triangle separately, and then I will figure out the area under the curve. So for my blue triangle, 1/2 base times height, I'm doing 1/2 -1 times 1/4. Wait. I don't know why I did 1/4. That was 1/2. Sorry. My brain was jumping to the answer. Look, and the double equal sign. Whoa. Okay, I need a sip of coffee. Hold on. Okay, I'm better. I'm back. For the big triangle, it was 3. See, and why did I put 1/4 on that too? Did anybody notice that? You guys gotta stop me when I write down stupid things, please.
I saw it, but like I was just letting you figure it out, you know.
Thanks, Alyssa. Don't let me write down silly things. I'll try. I'm working on it. Okay. So for this one, 1/2 base times height, 3 and 1/2 is actually 7/2, and the height was 7, so we end up with 49/4, and then the area, -1/4 plus 49/4 equals 48/4, or 12.
Wait, so we would use
We're literally finding the area of the two triangles. The one below the x-axis is negative, the one above the x-axis is positive, and we're adding them together.
Wait, can you show me
This part?
Yeah.
And then we're gonna write down, interpret the meaning, we're gonna write down in words what this means.
That's not the
Okay, so interpret the meaning. The net change,
It's the net change, the accumulation.
oh, in position, I heard a good word over there, which is also known as the displacement from time 0 to time 4 is 12 feet. So that meant my particle was moving left, moving right, and I'm not talking about the total distance that it traveled. I'm talking about how far away this point to this point ended up being. Displacement is just how far the ends are. Okay, so now let's look at this difference. So we're going to compare and contrast the value and meaning of this expression versus finding the area under the curve. If we're talking about finding the area under the curve, and we're simply just straight up talking about area, so this was our blue section, and this was our pink section. If I'm talking about geometry, area wants to be absolute value, and we want to add together those two things. So if I'm talking about the total area under the curve, would have to do the absolute value of 1/4 plus our 49/4. And I got those two values from up above the previous calculations. In that case, my area would be 50/4 or 12.5. And what calculation did I figure out here? Here's the difference. If I'm calculating that area, I'm actually calculating the total distance my particle traveled and not just the distance between the ends. So let me draw this picture. Here's my particle. It traveled here and then it traveled here. In my first problem, I calculated this distance. That was part C. The green stuff, all of this and all of this is from part E. And that would be our total distance traveled. From time equals 0 to time equals 4 is 12.5. Do we understand the difference between those two? It's tricky, gotta pay attention. Okay. So let's make a chart comparing some things. So if we are finding our integral from A to B of the velocity of t with respect to t, the area under the curve from A to B is the other version of this. So the integral and the area under the curve are not the same thing. Okay, so on the left, the integral from A to B is going to give us an answer that is the net change in position. The area under the curve is going to give us the total distance. If we're looking for an integral can be positive, negative, or 0. If we're looking for area is always positive. Any other comparisons you guys notice we want to add? No? I might put area under the x-axis is negative. And then use the absolute value of area under the x-axis. If we happen to use the absolute, actually let's not call it area. Use the absolute value of the integral for any part under the x, for the integral, whoops, that's not an s, integral of v of t dt under the x-axis. We can add to that if we think of anything else.
What is the dt there for?
So it's telling us with respect to time. If you have multiple variables, you can do an integral, but you have to know what variable you're supposed to be doing it with respect to. Here's the other thing that I have not explicitly said yet. Integrals are the opposite of derivatives. When you take a derivative and you write it as its differential form, dy equals f prime dx, f prime of x dx. When you integrate, you are getting rid of the dx and going back to your original function. And so the dx is part of that, telling you that you can take the integral with respect to x. Okay, we're going to do geometrically one more problem. Why don't you guys try this one without me? I'll be walking around if you need me. Sorry, I was playing to make everyone seasick on the monitor.
I know, I can't remember my graphs.
Did you take the picture I wanted you to take? Bless you.
Less?
Yeah. In that picture, yes.
Oh, when she.
But this is the graph of that.
Oh. I felt bad for her. She's like, okay. I was really excited. When you say you, if Mia calls, yeah. If I call her name and she's like, you get away. She's like, I cannot get sick. Oh wait, yeah, she does do that. She's like, you get away. What was he doing? You were supposed to be so.
So this one is asking us to evaluate the integral. Remember, above and below the x-axis, not left and right of the y. These are both above. It's all above, so these are both positive.
Because that's in out so extreme to your degree. Because the x-axis is going up 1 over 1 up. Yeah. Okay, but we can come up because that's. Oh, I don't know. But we have to like yeah. Oh, for the area. So.
Yeah.
Is this technically -2 or is the distance just still 2?
Okay, so when we were looking at this problem up here, the distance left and right, that we always measured positively. It's the area up and down if it goes below. Yeah, so think about it like, are you digging a hole or are you building a mountain? Right? So for this one, we have a hole first and then a mountain. But for this one, we have 2 mountains. Nothing goes below ground level. So these are both positive.